Technetium. There isn't much information about it on YouTube yet, but that would change in the future. Today we are going to talk about technetium in the environment. What can you expect from today's video? Where do we know this element from? Where does the element technetium come from? How did it get into the environment? And the reduction of technetium in the presence of carbonate to better understand the chemistry of technetium under environmental conditions. The nuclear isomer technetium-99m is well known for its use in nuclear medicine for diagnostic purposes. During its use, metastable technetium-99 falls into the ground state, emitting a 141 keV quantum, which enables diagnosis in nuclear medicine using SPECT. But the ground state, i.e. technetium-99G, or in the further course simply just technetium-99, is just as relevant as the 99M. It is not only relevant for chemistry, but also for the environment. It is one of the longest lived fission products produced in significant quantities during nuclear fuel burnup. I'm showing here only one of extremely many possible ways of nuclear fission. In nuclear power plants, the energy released during nuclear fission is used to boil water. What an invention. Uranium-235 or plutonium-239 are fissioned. So after the uranium-235 or plutonium-239 fuel in a nuclear power plant has done its job, we are left with a mixture of fission products and other elements, and after a certain decay period are then sent into final repository. Some fission products have such a short half-life that in theory we can just wait for them to decay, but others we cannot just wait, and one of them is technetium-99 with a half-life of 211,000 years. Over a very long period of time it will be one of the last relevant radioactive elements that make high-level radioactive waste radioactive at all. There is another graph similar to this one. Here the y-axis no longer describes the decay heat, but the radiotoxicity in sievert per megaton. In short, the emitted dose of the respective radionuclide. In any case, we can see here that after 200,000 years, highly radioactive waste reaches the order of magnitude of naturally occurring uranium ore. So it must be isolated from the biosphere for at least that long. Germany, however, says 1 million years, just to be sure. Now we have touched briefly on the nuclear technology part. Why am I telling you this? So that you understand where almost all technetium in the world comes from nuclear fission. And the most relevant application of nuclear fission is the nuclear power plant. But there are also research reactors and bombs in which nuclear fission also takes place. And now you're probably thinking that I want to move onto the topic of final repository. Yes and no. We have opted for a deep geological repository. This comprises a system with several different barriers designed to isolate the radionuclides stored in the canisters from the biosphere. This so-called multi-barrier system is intended to contain the radionuclides for at least 200,000 years. We have several different barriers that isolate it from the biosphere, i.e. the actual environment, and in doing so, scientists and the Federal Company for Final Repository must also deal with, among other things, how the nuclides behave when they are released from the first technical barrier, the canisters. In this video we do not deal directly with radionuclides and minerals, we do that in another video, but radionuclides have already been released into the environment. They are present in the environment both through natural means and through human activity, reprocessing plants, nuclear power plants, research, medicine, nuclear weapon testing, or other accidents. A particular legacy site in terms of radioactivity is the Hanford site. The Hanford site is where radioactive waste from the Manhattan Project is collected and handled, including large quantities of technetium. The source cited here provides a nice overview how much technetium is released during a fuel cycle, for example. There is a table that refers to a fuel cycle of a light water reactor with an electrical output of 200 megawatts. Another piece of very crucial information here. No technetium is released during reactor operation itself. For contextualization, the following values are available. Weapon tests released 10 to the power of 14 becquerels of technetium, and reprocessing in general released 10 to the power of 15 becquerels. An additional 10 to the power of 7 becquerels per year is released in the context of medical applications. And the Hanford site mentioned before released 3 times 10 to the power of 13 becquerels. These values date from before the 2000s. Another way in which technetium entered the environment was through nuclear weapons testing. With a total of 140 terabecquerels, this is at least a noteworthy amount. So technetium enters the environment in many ways, both intentionally and unintentionally. And there, this element can of course also react chemically, and the chemistry of technetium is very diverse. We may be familiar with the amazing chemistry of manganese, which is found directly above technetium in the periodic table, and, depending on the oxidation state, produces many bright colors in solution. Technetium does this too. Although it must be said that manganese and technetium are not as similar as you might think. In their chemistry, technetium and rhenium are a bit more related to each other. But most people aren't familiar with rhenium chemistry. Technetium can be in the form of many different oxidation states ranging from +7 all the way to -1. Of these, only the technetium 7+ is stable in water as a pertechnetate ion, which is extremely mobile and water soluble. And there's also technetium 4+, which tends to form poorly soluble technetium dioxide hydrate in water. The big question we are asking ourselves today is, yes, okay, technetium can react chemically, but what chemical reactions can dissolved technetium cause in the environment? If you look at the Pourbaix diagram for technetium, it looks something like this. Potential has been plotted against pH value, and you can see that in aqueous solution under environmental conditions where the pH is between 6 and 8, you have either this pertechnetate or the dioxide hydrate. This is where the TecRad group led by Dr. Mayordomo comes into play. Because they thought to themselves, okay, we can't model complex environmental chemistry that easily, but we can do so in a model that comes somewhat closer to the environmental conditions. So they took a look at technetium chemistry in other media, specifically in carbonate-containing media. The carbonate ion is a bidentate ligand. This means it can surround the technetium atom and thereby stabilizing other, somewhat more exotic oxidation states. Even some oxidation state one might not expect to be stable in nature based on these idealized experiments usually conducted in the laboratory using just distilled water and such. Carbonate is found almost everywhere in nature. Lime, calcium carbonate. Shells and other components of sedimentary rocks, calcium carbonate. And also metabolites. So you and I and every other person exhale CO2 as a so-called metabolite. It's a very normal metabolic product. And here, for example, that becomes carbonate again. Calcium carbonate. So carbonates and CO2 are everywhere. The following experiments are based on a paper linked in the video description called A Spectrochemical Study of the Technetium 4-Technetium 3 couple in Bicarbonate Solution. New findings from Dr. Mayordomo's working group will follow soon. Then off to the laboratory. Unfortunately, it's not just CO2 that's everywhere, but oxygen too. This has to be removed from the solution very carefully, as otherwise it could interfere with the electrochemistry, bubbled out by just using a stream of nitrogen. Absolute caution is required here, as the last thing you want is for the potassium pertechnetate solution to splash around in the glove box. This is why that has already been prepared, and what we see here is only the inactive sodium carbonate solution. Here's the finished potassium pertechnetate solution, in which 0.5 millimoles of the radioactive salt has been dissolved in 0.5 molar sodium carbonate solution, all at the pH value of 9.3. This will soon be placed in a very elegant system. This here. Yes, it doesn't look that exciting, but it's a UV-Vis spectrometer cell with connection for electrodes, so that you can continuously record a UV-Vis spectrum during electrochemistry. A light is sent through this cell via fiber optical cables from the right to the left. The cables themselves have their own connection to the glove box. A carbon electrode is used for the electrochemical process. A platinum wire is used as a counter electrode and a silver chloride electrode as a reference electrode. First, 2 of the 3 electrodes are connected, and before we can start the measuring, we have to record a blank, as with any UV-Vis spectrum. In other words, it's just a background measurement. This is done with the sodium carbonate solution that has just been bubbled through. Once the carbonate solution has been measured as a blank, it can just be pipetted out, because now it is time for the carbonate-containing technetium solution. Dissolved pertechnetate ions do not cause any color change in the solution. Here's a little digression. The well-known permanganate ion causes a purple color impression in solution. This is because the molecule can absorb yellow light. When yellow light is absorbed, the complementary color remains, which is in this case purple. Manganese itself does not have any directly excitable electrons. Excitable electrons are needed for a compound to interact with light at all. And then, ideally, these electrons should be so easily excitable that they can interact with light in a visible range. We as humans don't care if something is missing in the UV range. So we need valence electrons. At first glance, manganese in this compound does not have any valence electrons. The effect that gives us excitable electrons again is called the charge transfer effect. In the transition groups, we can see a trend where the stability of the highest oxidation state increases downwards. Manganese 7 plus is very small and has a high oxidation potential. It therefore draws electron density away from the oxygen atoms, which means that excitable electrons are available again at the manganese atom. This is not the case with technetium 7 plus. Compared to manganese 7 plus, technetium 7 plus is a milder oxidizing agent. The electrons in pertechnetate can be excited with shorter waved UV radiation because technetium is larger and softer, which reduces the charge transfer and makes pertechnetate and perrhenate colorless. During electrolysis, the technetium in the pertechnetate is then reduced. With a potential of minus 0.95 volts, it is possible to give the technetium 4 electrons. This puts it in the oxidation state plus 3. This is extremely unstable in a normal aqueous solution. But let's see about that. After several hours of electrolysis, a green solution can be obtained. Here the technetium is stabilized by the carbonate ions contained in this sodium carbonate buffer solution. It immediately oxidizes to the 4 plus at the first opportunity, but it can be stabilized in a nitrogen atmosphere. Fortunately, Arkady, who carried out the experiment for this video, took a screenshot of the UV-Vis every half hour, and now you can clearly see how the transmission in the red range slowly decreases, and since the complementary color to red is green, we have a green solution. The whole process also works with a slightly lower voltage of minus 0.74 volts, whereby the technetium is then reduced from 7 plus to 4 plus. Nuclear chemists usually refer to 4 plus as the second relevant oxidation state of technetium in the form of a dioxide hydrate. However, we see that we do not have a brown precipitate of technetium dioxide hydrate, but rather a reddish solution. Here we have technetium 4 plus in solution. The exact species in which it is present has not been characterized yet. There are suggestions in the literature that it could be a carbonate-containing dimer, i.e. compounds with 2 technetium units. Is this relevant now? Yes, because with the 2 experiments, i.e. the reduction to green technetium 3 plus and pinkish technetium 4 plus, we were able to demonstrate several things at once. At the beginning of the video, I talked about technetium 7 plus as a pertechnetate ion and technetium 4 plus as a dioxide, and that these were the only oxidation state relevant to the environment. I even justified this using the Pourbaix diagram, but this was only half the truth, because the diagram was not really intended to represent the real environmental conditions. In a reductive medium in the environment where carbonate ions are present, technetium potentially distributed in the environment as pertechnetate ion does not have to be reduced to the hydrated technetium dioxide. The water solubility of the dioxide is much lower than that of the pertechnetate, at around 190 becquerels per liter. Although this is not negligible, it is very low. And here we have the new Pourbaix diagram that includes carbonate ions. And now we know that reduced technetium in the oxidation state of plus 4 can still remain as a quite mobile complex due to the presence of carbonate ions, and thus remains mobile despite its reduction. Of course, provided that these do not interact with the surrounding minerals again. In addition, carbonate ions in an even more reductive medium can stabilize even the oxidation state of plus 3. This is an oxidation state that has been neglected for technetium in the context of environmental chemistry. So in summary, in this video we have now taken a more realistic look at the environmental chemistry of technetium when carbonate ions are present, which they are in the environment. Technetium alongside carbonate is in the environment. Whether the technetium got into the environment intentionally or unintentionally, it is now very important to understand the environmental chemistry of technetium and to later exploit this knowledge to our advantage. With that being said, a big thank you goes out to Arkady, who kindly did the experiment for today's video. And of course to Dr. Natalia Mayordomo, head of the TecRad Junior Research Group at the Helmholtz Center Dresden-Rossendorf. And of course to my patrons for their financial support. With that being said, thank you for your attention and goodbye!